The detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, stands as one of the most monumental scientific achievements of the modern era, confirming a prediction that Albert Einstein made a century earlier and opening an entirely new window onto the universe. This discovery was not merely the confirmation of a long-held theory. It was the first direct evidence that the fabric of spacetime itself could ripple, bend, and shake, fundamentally validating the four-dimensional model of the universe that Einstein had proposed. In his theory of general relativity, Einstein posited that time and space are not separate entities, but form a single, unified continuum known as spacetime, where space is three-dimensional and time forms the fourth dimension. According to this revolutionary model, gravity is not a force in the traditional sense, but the warping of this four-dimensional spacetime fabric by mass, and when massive objects accelerate, they send ripples through this fabric, gravitational waves. The LIGO detection of gravitational waves generated by the collision of two black holes, one approximately 29 times the mass of the Sun and the other about 36 times, provided the most powerful evidence yet that this four-dimensional spacetime is not merely a mathematical abstraction, but the actual structure of our universe. The connection between gravitational wave detection and the fourth dimension extends far beyond the simple confirmation of Einstein's spacetime model. It has opened up new avenues for testing the very structure of spacetime itself and exploring the possibility of dimensions beyond the familiar four. One of the most direct applications of gravitational wave astronomy is the ability to constrain theories that propose the existence of extra spatial dimensions. The landmark event GW170817, a gravitational wave signal from a binary neutron-star merger that was also observed in electromagnetic waves, provided a unique opportunity to test whether gravitational waves and photons experience the same number of spacetime dimensions. In models that include additional non-compact spacetime dimensions, gravitational waves would leak into these extra dimensions as they propagate, leading to a reduction in the observed amplitude of the waves and a commensurate systematic error in the inferred distance to the source. By comparing the distance to the source inferred from gravitational waves with the distance inferred from the electromagnetic counterpart, researchers placed stringent limits on the number of spacetime dimensions. The analysis constrained the effective number of spacetime dimensions experienced by gravitational waves to be d equals 4.02 plus 0.07 minus 0.10, and d equals 3.98 plus 0.07 minus 0.09, depending on the Hubble constant value used, conclusively demonstrating that gravitational waves propagate in d equals 3 plus 1 spacetime dimensions, as expected in general relativity, and placing strong constraints on theories with extra dimensions. The study of black hole collisions in higher dimensions has also provided fascinating insights into how gravity behaves when additional spatial dimensions are present. The high-energy collision of black holes has been simulated in up to 8 spacetime dimensions, revealing how the energy radiated in gravitational waves varies as a function of dimensionality. These simulations have shown that the fraction of mass converted to gravitational wave energy is lower in higher dimensions. For head-on collisions approaching the speed of light, the energy lost in gravitational waves is predicted to be about 12.9% in 4 dimensions, 10.1% in 5, 7.7% in 6, 5.5% in 7, and 4.5% in 8. This dependence on dimensionality has important implications for models of TeV gravity and large extra dimensions, where the fundamental scale of gravity could be as low as 1 TeV, potentially allowing for the formation of black holes in high-energy particle collisions. The study of higher-dimensional black hole collisions is not just an academic exercise. It provides a window into the physics of possible extra dimensions and the nature of gravity at the highest energies. The energy released in black hole mergers, even in our familiar four-dimensional spacetime, is so vast as to be almost incomprehensible. The collision of two stellar mass black holes, each about 5 times the mass of the Sun, emits more energy in gravitational waves in less than a second than the Sun will emit in 7 trillion years. For a brief moment, these black holes emit more energy than the light from 1 billion galaxies full of stars. When supermassive black holes collide, those with masses of hundreds of millions of solar masses. The energy emitted in the final seconds is thousands of times the combined energy emitted by all the stars in the visible universe over the same period. Yet despite these mind-vaporizing energies, gravitational waves from such events are nearly undetectable by the time they reach Earth, weakened to less than a whisper by their unfathomable distance. Future space-based detectors like the European Space Agency's Laser Interferometer Space Antenna, LISA, mission are expected to provide much more data on these colossal events in the coming decade. Gravitational wave astronomy also offers a powerful tool for probing the fundamental structure of spacetime through the study of primordial gravitational waves, ripples in spacetime generated in the very early universe. One of the more exotic theories that can be tested through gravitational wave astronomy is the idea of vanishing dimensions, which proposes that at higher energies, the number of spatial dimensions reduces from 3 to 2 or even 1, potentially solving problems in quantum gravity and the cosmological constant problem. A key feature of this framework is that in a 2 plus 1 dimensional universe, there are no local gravitational degrees of freedom, and hence no gravitational waves can exist. If the universe was indeed lower dimensional at some earlier epoch, there would be a maximum frequency for primordial gravitational waves related to the dimensional transition scale, beyond which no waves can exist. This suggests that gravitational wave detectors could be used to probe this novel framework, looking for a cutoff in the primordial gravitational wave spectrum. The connection between gravitational waves and the fourth dimension is also being explored through theoretical frameworks that propose a universe with more than 4 dimensions. One such model proposes a single eternal 4D Euclidean dynamic manifold, where the coordinate t is treated as a spatial coordinate, and quantum mechanics, gravity, and accelerated expansion emerge as projection artifacts onto a locally biased hypersurface. This framework resolves the measurement problem, the black hole information paradox, and the Hubble tension, and it predicts distinctive, near-term testable signatures, including gravitational wave echoes with relative amplitude 10⁻³ which could be detected by future gravitational wave observatories. Other researchers have proposed that the speed of gravitational waves may provide evidence for a pentadimensional universe, for spatial and one-temporal dimensions, based on formulas suggesting that gravitational waves actually travel in matter. These proposals remain speculative, but they highlight the rich interplay between gravitational wave physics and theories of extra dimensions. The study of gravitational wave memory, a persistent distortion of spacetime after the passage of a gravitational wave burst, has also been advanced by recent research. A new analytic model of the total energy emitted in the head-on collision of 2 equal-mass black holes has been developed, based on the lowest quasi-normal mode of the final black hole marking the end of the low-frequency domain. With no free parameters, this model predicts that in the speed of light limit, 13.8% of the total initial energy is emitted in gravitational radiation, in good agreement with numerical relativity. This model also enables calculation of the nonlinear contribution to the memory. As numerical relativity simulations continue to improve, these models can be tested for increasingly relativistic speeds, providing deeper insight into the extreme physics of black hole collisions and the nature of gravitational waves. The detection of gravitational waves and the study of their properties have thus become a powerful tool for probing the fundamental structure of spacetime and testing theories of extra dimensions. From constraining the number of spacetime dimensions to simulating black hole collisions in higher dimensions and searching for primordial gravitational waves, gravitational wave astronomy is providing unprecedented insights into the nature of gravity and the universe. The ability to hear the ripples in spacetime has opened a new era of exploration, one where the fourth dimension is not just a concept in a physics equation, but a reality that can be observed and measured. As gravitational wave detectors become more sensitive and new missions like LISA come online, our ability to probe the hidden dimensions and the nature of spacetime will only grow. The journey from Einstein's prediction to LIGO's detection has been a century-long odyssey, but it is only the beginning of what promises to be a new age of discovery, one where the fourth dimension and the fabric of spacetime itself become accessible to our instruments and our understanding.